Hi, I'm Professor Angela Rasmussen from the Department of Electrical and Computer Engineering at the University of Utah, and today I'm going to be going over a BJT AC analysis. So this is going to be the circuit that we're going to look at. You're given these parameters, and you're also given RPi1 and GM2, but not RPi2 and GM1. So you need to use that information to solve for those values. So first off, we want to find GM1 from the RPi1. So we know that GM1 is related to RPi1 by beta over RPi1. So beta is given here as 100 over RPi1, which is 2K. So that gives a value of 0.05 amps per volt, or 50 milliamps per volt. And then RPi2 is also related to GM by beta over GM. And so we get 100 over 0.5 milli for a value of 200K ohms. And so we can use these two values in our solutions. So now we want to find the Rn input. So we're going to look at this circuit, and Rn we can see, remember when we're looking for resistance, we can use the resistance reflection rule to get rid of, can't figure out where to point to it, that GM1 Vpi1. And so looking at just getting rid of that portion here, so we want to ignore this. We need to find our location. The location for resistance is going to be the node you're looking at, which is in the emitter side. So emitter to base means that we're going to divide base resistances by beta plus 1. So the pathway here then is Rn is 1K plus RPi1 plus 40K, all of that over beta plus 1. By using the beta plus 1, we can ignore this. And we can plug in now our RPi1 was 2K. And we can get the value for RPi1, or Rn, which is 1416 ohms. So this will be our Rn value. Our Rout value is again going to be from the node we're looking at to ground. And so we have different branches from this node itself. So we have two splits here. So we're going to have 20K in parallel to everything onto the left of the Vout node. So our out is going to be 20K in parallel to whatever is in that branch. So we can see, hard to read, so I'm changing this to white. So our out is 20K in parallel with that branch. And so we have, again, we go here and we have a split. And as we go through the 3K, we see that we're on the top of this dependent source. And to prove that that is an open, remember to go back and look at the Thevenin equivalent for the dependent sources. So looking at that from the top is an open, so we can ignore the 3K as a floating wire, and therefore we only need to account for the 15K. So that branch will be 5K plus 15K for that to be in parallel. 20K in parallel with 20K is going to give you 10 kiloohms. So our out will be 10 kiloohms. So now we want to find the gain, the overall gain, which is going to be V out over V sig. So I'm going to look at the V out node and write an equation for the V out node. So I'm going to erase these for a minute. So now when I'm looking at an equation, I'm going to find an equation for VO. And so VO, if I can find the current in this branch, I can just use Ohm's law and find current times resistance. So V out will be that current, I times 20K. And I is going to be a current divider from GM2 as my source, and then I'll have these two branches will have current from that. So that current equation will be a minus GM2 V pi 2, and the opposite branch there will be 15K all over. 15K will be the one branch, and then the other branch will be 25K. So that will be my current, and then I multiply it by 20K. Which is hard to read there, but that's multiplied by 20K. So plugging in the GM2 value, this ends up giving me a value of minus 3.75 V pi 2. So now I need an equation for V pi 2. I'm going to look here at V pi 2. And V pi 2 is located here in the middle. And I have two sources. I have the GM1 V pi 1, and I also have that GM2 V pi 2. So again, I mentioned in class that I would use a kind of a rule of thumb is that you're going to remove the transistor that you're looking at's dependency. So that would mean that I want to ignore this one. And so I'm going to look at the other one as my source. So that means that this would be my source location. So here I would determine this as my source location being in the base. And from there, I'm going to reflect the emitter resistors by multiplying them by beta plus 1. So now this is my new circuit. Again, it looks like if I find the current in this branch, I can take that current and multiply it by R pi 2. So this is a little bit smaller. So V pi 2 is a minus GM1 V pi 1. Branch opposite would be 2K all over. One branch is 2K. The other branch has 1K plus R pi 2 plus 20K times beta plus 1. So this is all the resistance in the other branch. So this is all the current, and then I need to multiply it by R pi 2. So this would be my equation for V pi 2. I can plug in all these numbers. So GM1 we found to be 0.05, and R pi 2 we found to be 200K, and beta is 100. So we can plug all these in, and for this one we end up with a approximately minus 9 V pi 1. So multiplying all those numbers together, I got approximately minus 9 V pi 1. So now we need an equation for V pi 1, and V pi 1 is located in this transistor. I'm going to remove these for a minute. So now things are a little different because now I'm not using the other one. So here, this transistor's dependent source is going to be the GM1, so I'm going to try to ignore that and look at the other source, which will be the VSIG, meaning I'm in the emitter side. So in the emitter side, I again would multiply all those, divide them by beta plus 1. And I have a voltage divider here. And then I notice this is plus to minus. So I'm going to have an opposite for the voltage, so it would be a minus voltage for V pi 1. So I get minus V sig times R pi 1 over beta plus 1. And then I would combine all of those in series. And it was 40K over beta plus 1. And I multiply this out, I get a minus 0.01398. And now I can plug back into this V pi 1. So I use this number into V pi 1. I get that number and I go back and plug that into my V pi 2 to get my value for V out. And so V out here is going to be that minus 3.75 minus 9 from the V pi 2 and then a minus 0.01398 V sig. Sorry, I forgot to write V sig here. And then I can bring the V sig over to this side, just divide it on both sides to get my V out over V sig ratio. And now multiply all this out, gives me a minus 0.5 volt per volt. And that would be my gain, which you can see here is very low and not ideal. All right, this gives you an example though of the AC analysis.